Okay, we're going to continue on here, chapter 12, I think. Hmm. So we've been talking obviously about kinetics in this chapter, and last time we talked about really how to calculate the rate law from basically data that's given to you, which is very often how you do calculate a rate law. Again, a rate law is a little bit different than, say, a rate expression, as it will only be concerned with reactants. So again, only reactants basically involved. Again, these orders on top, as we talked about, are sort of the proportion that you need of these guys to sort of yield a specific rate. And it's all found pretty much experimentally. So as we saw, you basically will be given usually a table that has some concentrations of everybody. And you also have some rates or initial rates given to you for a number of different sort of experiments. And mathematically, you basically want to kind of choose two entries from that table where you're going to compare basically their concentrations and their rates. And the idea here is you just want one unknown. So when you do go to that table, as we did a number of those examples, you would want to be looking for perhaps where in this example, maybe A stays the same, but B varies. And you can put it in there and you'll get your something like, 2 to the X equals like 2 or something like that. And you can then solve, for example, the order there, which in this case would be 1. A reminder, if you don't really have really pretty numbers, or maybe you did a smaller rate on top and larger one on the bottom, you may get some type of decimal number that it may not be obvious to you what the value of X or Y may be. So you can always just natural log, once again, both sides, and then divide that to the other side. And that will again give you 1 in this particular example. So again, if you don't get really pretty whole numbers or something like that, or you get decimals, again, just natural log both sides, divide it out, and you'll be able to solve for your order in that particular case. You want to obviously then after you do that, you want to go back to the table. And for example, in this here, we'd want to keep B constant and maybe vary A, and you can do the same thing. That will allow you to get to the orders here of the individual reactants. You could also get the overall order by adding them together. And once you do have pretty much the orders for the rate law, you then could actually use the information to calculate the value of the rate constant. And once again, you would choose any of the entries in the table. They all should give you basically the same K value when it's all said and done. You obviously just can't mix and match. So, whichever one you choose, got to use all the information from there. Any questions on any of that stuff there from last time? All right, so I think this is where we laid up. So we're going to now talk about 3 very common orders of reactions, and that is first order, second order reactions, and zero order reactions. And for the most part, these are the most common sort of reactions that occur. And just think about it sort of logically, in a sense that if you think about a lot of the chemical reactions that you probably have seen over your chemistry career here, when you look at those equations, they probably have maybe 1 reactant, maybe 2 reactants, occasionally maybe 3. They usually don't have, 4, 6, 5 reactants happening at once. And if you think about sort of the orders of each of those reactants, again, commonly you're going to end up with perhaps a first order overall reaction, a second order, a zero order overall reaction. Again, if you're against giant super orders for the overall reaction, you probably would need a good amount of reactants there to happen. So first order, zero order, and second order reactions are very sort of common ones. So we're going to start with first order reactions. And obviously you can achieve a first order reaction really in 2 ways. You again could have pretty much just 1 reactant, where obviously the order of that reactant is first order. Thank you. You can also have perhaps 2 reactants where 1 is first order and 1 is zero order, right? So that would also give you an overall first order sort of reaction. If you write the rate law here for a first order reaction like we see here, and we rearrange it and actually solve for the K, we see the typical units, as I probably was talking about as we are going through some of those examples last time. The typical units associated with a first order reaction rate constant is 1/seconds or reciprocal seconds. Truthfully, it does not have to be seconds. It could be any unit of time. So it could be like 1/days, 1/weeks, years, whatever it may be. Usually we associate reciprocal seconds with it because much like in the lab, you're probably not going to sit there for days doing an experiment. So a lot of times we measure time in like experiments in seconds. So that's a very common sort of time unit that we use when we do experiments. But technically speaking, it really is 1/some unit of time would indicate that it is a first order reaction. So that's really important to understand. Now, when we have a first order reaction, we have what is sometimes referred to as the integrated rate law. And that is a rate law here that basically looks at both concentration and time dependency on each other. So this is sometimes referred to again as the integrated rate law. It is basically the relationship of time versus concentration and how it's changing. And that is for a first order reaction, the natural log of A. A is kind of like if you want to think about your final concentration equals the natural log of A naught. The A naught, and naught is like that little circle on the bottom there. That is like the initial concentration. K here is actually the rate constant. And T here, which gets some used to, or people need a little time to get used to it sometimes, is at this point, they automatically, usually when they see T, think temperature. That's not temperature, that is time in this case. So just keep that in mind. Obviously, temperature would be capital T, but here is lowercase t, which is actually time. So that's a really important thing. Sometimes people always see T and just think temperature automatically. Also really important are the units of K and T. As you can see, you're going to be multiplying them together. So the unit of time needs to actually be the same in each of those. So it is possible you could have time in like days, and maybe your rate constant's in like seconds or hours or something like that. So you do always want to make sure that when you're using K and T in this equation, for example, or really any of these sort of equations we're going to see, you want to make sure that that time element is the same in both, so everything properly cancels out correctly. Now, this is a typical graph that you could see for a first order reaction. It shows the concentration of A over time, and as you can see here, as time goes on, we would expect A to start to decrease with time. But when we do kinetics, for the most part, we're interested in more of a linear relationship with all these things. So we can take this integrated rate law here and rewrite it as the natural log of A is equal to minus KT plus the natural log of A naught. And when you rearrange and write this equation in that form, that is equal to y is equal to mx plus b. That is basically the equation for a straight line, and that's going to give you your linear relationship. It will also give you the graph that we most often associate with a first order reaction, which is this graph over here. And you can see on the y axis there, you should have the natural log of A. On the x is time. And that should yield you an actual straight line. So there should be a linear relationship when you graph those two things together. And you will get here that the slope of this line will equal minus k. And that is because the slope of this line that we see right here in the graph, is that a positively sloping line or a negatively sloping line? It's negatively sloping line. So the slope value here is actually going to be negative, and that negative will turn your k value once again into a positive number here. So the slope equals negative k. That will turn your slope into a positive rate constant, which is again what you should have in this particular case. There is also, as we will see, but I'll pop it up here with all the other stuff on this one, a half-life equation for first order reaction. And the half-life equation is the natural log of 2 divided by the rate constant. Natural log of 2 is 0.693 on your calculator if you punch that in, divided by the rate constant. The half-life is the time it takes, much like the name implies, for half of whatever you got to go away, basically, and decompose, if you will, or decay. And obviously, after the first half-life, if you had 10, you'd have 5. After the next one, you would have 2.5. After that, I need a calculator, but you keep dividing by 2, basically, and whatever is left at that point. So for a first order reaction, the information on this screen is quite important. So once again, the units associated with the rate constant is really important because, as I mentioned before, not a lot of times in problems will they just, like in flashing lights, tell you, hey, this is a first order reaction. Sometimes they may, but a lot of times they will not do that, but they will give you the value of the rate constant. And you're supposed to know by just looking at the units, oh, those are the units that we associate with a first order reaction. And because of that, we then should use, obviously, our first order reaction sort of formulas here. And the integrated rate law, you should know the half-life equation, and you actually should know the graphs that are associated with it. Once again, this graph over here on the right is probably the one that you see the most, but the graph on the left also is a first order graph as well. Any questions on that? First order reactions are important as well. We will actually see them later on in the semester when we get to nuclear chemistry. All radioactive decay basically follows first order kinetics. So all radioactive particles that continue to decay will decay in a first order sort of situation. Any questions on that there? We will also see when we get to that chapter as well that although it is the natural log of A equals the natural log of A naught, and it is the concentration of A, which is typically what we use in this chapter with kinetics. We typically do use concentrations. It actually does not need to be concentrations as long as those units are the same. You could do it, for example, in grams and grams, milligrams, milligrams. You could do it in rates on each of those. You could do it in anything as long as A and A naught are in the same units. It will work out correctly. But I would say in this particular chapter we're currently in, probably molarity is most often what you're going to be using when you kind of pop it in there. We also see with the half-life equation there, it is not dependent on the initial concentration of the substance there. It is really just dependent on sort of the rate constant there. All right, so why don't you take a try on this here and see what you get. The reaction of 2A that goes to B is first order with A, has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds at 80 degrees. How long will it take for A to go from 0.88 to 0.14 molars? Take a few moments there to see what you come up with. Okay, so let's take a look, see how you're doing. So a couple of things here. They're nice enough to tell us that is first order. Probably doesn't happen a lot, but we would know that is first order, right? Because we do have the rate constant given to us. And again, we see those units, and that tells us that it is a first order reaction. That also, again, should tell us that we should use our integrated rate law for first order. Natural log of A equals natural log of A naught minus KT. In this case, obviously, we have our rate constant 2.8 times 10 to the minus 2 reciprocal seconds. We have our initial concentration here, which is 0.88 molar. We have our final concentration, which is 0.14 molar. And at that point, it's pretty much everything we need. So that's going to get us here the natural log of 0.14 equals the natural log of 0.88 equals minus, kind of like equals, but not so much, minus our 2.8 times 10 to the minus 2 reciprocal seconds and our t in this particular case. Now we want to make sure we kind of punch it in correctly. So personally, if I was to do this, which I'm going to do right now, I would take the natural log of 0.14 and hit equals. I then basically will be subtracting that guy to the other side and minus the natural log of 0.88 and hit equals. And if you do that, I will then get minus 1.838279 equals negative 2.8 times 10 to the minus 2 reciprocal seconds and time. We're then going to divide that to the other side along with the negative as well. And that will yield us here, as we divide it, our seconds will pop to the top, and maybe a little 66 seconds in this particular case. Any questions on that there? So again, mathematically, you want to make sure you are punching these in correctly to your calculator. Again, sometimes people struggle with sort of rearranging it. It is also, natural log of A, not over A, and you could kind of do that as well and separate it, but this is probably the easier way. All right, so we talked a little about half-life. Again, the half-life is the time it takes for half of whatever you started with basically to go away. And for the first order specifically, it is the natural log of 2 over the rate constant. Once again, in some problems, very commonly in kinetics type problems, you will need to use both the integrated rate law, for example, and the half-life equation sometimes together. So sometimes you will be given problems, for example, and maybe you're looking for, how much time, or maybe you're looking for a concentration, but you have everything there given to you except for maybe K, the rate constant, but they will give you the half-life. And you could use the half-life obviously to solve for K and then pop it into there. So if you feel like you're missing something, but they kind of give you that half-life sort of information, you oftentimes will use the half-life equation to get the rate constant and then use the rate constant into the integrated rate law. So very commonly, do you have to use sometimes these two equations together? And that's usually the case of what happens, again, especially if they give you sort of the half-life. All right, so what is the half-life of N2O5 as it decomposes a rate constant of 5.7 times 10 to the minus 4? In this case, we could go right into our half-life equation. Natural log of 2 divided by K. Natural log of 2, again, is 0.693 divided by R, 5.7 times 10 to the minus 4 reciprocal seconds in this case. And that's going to get us a natural log of 2 hit equals divided by 5.7 exponent negative 4. Going to give us something like maybe 1216 seconds, 1200 seconds, whichever way you want to go there. And in this case, I knew it was first order because of what? Yeah, I knew it was first order because of the units associated again with K. Again, 1 over some unit of a time is going to be basically your first order sort of kinetics. Yeah. Any questions on that there? Okay, so let's try a couple more here, maybe. As we take a look here at our half-life, again, we can see we started with a bunch of circles. We lost half of them. Then we lost another half and another half. After about 10 half-lives, pretty much is gone at that point. Why don't we try this one? The reaction here of SO2Cl2 goes to SO2 plus Cl2 is first order with a rate constant 2.9 times 10 to the minus 4 reciprocal seconds. What is the concentration of SO2Cl2 at 865 seconds when we initially started with 0.0225 molar? They were, again, nice enough to tell you, but again, if they did not tell you that it was first order, right there is what should tell you that is first order, those units that are again associated with the rate constant. That should once again point you in the direction of our integrated rate law here for our first order reaction. Here, obviously, again, we do have the rate constant given us 2.90 times 10. I think that's a minus 4 I scribbled over. In this case, we're actually looking for really the final concentration. We do have the initial concentration, which is 0.0225. And we do have the time in this case, which is 865 seconds. So in this case, we basically got everybody on the right-hand side. We also see that unit-wise, in terms of the time aspect, we're actually okay here. That's in seconds, that's in seconds. So again, those are going to cancel out correctly, but it is very common that they are in different units. So that's something that you want to make sure you watch for. We'll pop that in there. That's going to give me the natural log of A is equal to the natural log of 0.0225 minus our 2.9 times 10 to the minus 4 and our time, which I actually do have, not T. So 865 seconds. We'll just turn that into a bad looking parentheses there. At this point here, we can really clean up our side here on the right, and that's going to give us the natural log of A. And again, I'm going to go natural log of 0.0225 hit equals minus 2.9 in parentheses to the negative 4 times 865. That's going to get me something on the right-hand side of negative 4.04509-ish. To get rid of the natural log there on the left, we need to take the inverse of the natural log, or the E there, if you will. And that's just going to get rid of that. And we're basically going to take that guy right there in there. So we're going to hit the right button on the calculator, probably. There we go. Try that one. And if we do that, we will end up with 0.0175. This does need some units there, as it is a concentration, so it is molarity in this case. First off, any questions on the calculation there? Does make sense. Why does it make sense? Concentration went which way? Down, which it should do, right? Because the final concentration should be decreasing with time. So if you did this and you ended up with a higher concentration you started with, your reaction is going backwards. Yeah, not really going right in the correct direction in that case, right? So again, it should make that. By the way, if you calculate the half-life, it's like 2,300 seconds or something like that. So that's before the first half-life. So we definitely should have more than half of it left right at this point, which we do as well. So again, those are things you can kind of look at to see if maybe, didn't calculate it correctly or not. Any questions on that there? All right, let's try another one here. Molecular iodine dissociates with a first order rate constant of 0.271. What is the half-life? You see our first order units there for our rate constant. And in this case, we're actually just looking for the half-life, so we can just pop it into our half-life equation that goes with our first order. So again, natural log of 2, 0.271 reciprocal seconds. And in that case there, we will end up with, looks like maybe 2.56 seconds in this case. Yeah, pretty quick. Every 2.5 seconds, half of what he adds is gone, right? So that's pretty fast. Yeah. Any questions on that there? All right, then let's talk about some other orders of reactions. The next type of order reaction we're going to talk about is second order reactions. And second order reactions are obviously different than first order reactions. And there's kind of two ways as well, or maybe more than two ways, that you could kind of get to a second order reaction. You could have one reactant where it is second order within that reactant. You could have two reactants where one is first order and the other one's first order. That will give you an overall order of two. You could also have, again, mainly the two ways probably. If we have our rate law here, which is the rate is equal to K times A squared, solving for K gives us the units that we associate for our second order, which I think we saw in a number of examples the other day. It is 1 over molar seconds. So 1 over molar seconds are the typical units that we associate with a second order reaction. Again, in terms of the time part, it doesn't have to always be seconds, but it does need to be some unit of time. So again, it could be like 1 over molar minutes or something like that. That also would be considered a second order. But 1 over molar seconds are the common units that we see. Again, that can be written as m to the minus 1, s to the minus 1 as well. By the way, as I might have mentioned last time, when we look at the units for the rate constant, which are 1 over seconds for first order, That's just like 1 unit, which is, what we got there. This is 2 letters, second order, right? It's a good way to remember that. For a second order rate law, we do have an integrated rate law, and it is this one right here, and that is 1 over the final concentration is equal to 1 over the initial concentration plus KT. Just like our first order sort of rate law there, we can rearrange this equation and take 1 over A is equal to KT plus 1 over A naught. And when you do that, that will give you basically this equation in the form of a straight line. Y is equal to mx plus b. That would mean on the y-axis here, we will actually graph 1 over the concentration. On the x, we will graph time, and that will again yield you a straight line. In this case, though, our straight line actually has a positive sloping line, right? So it's gone in a positive direction. So in this case, the slope actually does equal the rate constant. And so this will give you, again, a positive value for K, which is what you're looking for. And everybody in that equation is the same as it is in the first order one. Once again, that is your final concentration, your initial, your rate constant, and also your time. So they're all the same sort of values, if you will, in all of these equations. We also have a half-life equation here for a second order, and that is 1 over K. And 1 over K times the initial concentration. I'll get that there. And it is affected, as you can see here, by the initial concentration. So unlike a first order reaction in terms of the half-life of a second order reaction is affected by the initial concentration. How does it affect it? I don't know. We could just throw some numbers in maybe and see. If we took 1 over, say, 20 versus 1 over 10, we'll end up with maybe 0.05, and 1 divided by 10 is 0.10. So what we see here, right, is as the initial concentration actually decreases, what happens to the half-life? It actually will increase, yeah? So that's what we see here. By the way, I didn't put any K because K is constant in both of them. They'll be the same number, right? So you can kind of see here, as we lower the initial concentration, the half-life gets bigger or larger, I guess. And as the concentration gets larger, it gets smaller. Again, because we have less to start with, so it'll come off a little quicker. So once again, in terms of the second order reaction, we do see what you need to know. Again, those units of the rate constant is important to identify what it is. The integrated rate law here, our half-life equation, and once again, this is our typical graph that we see for a second order reaction. When we get to like the second kinetic experiment, you'll make 400 of these graphs, so you'll be used to them by then. But that is the one, again, that we associate with our second order. The last type of order of a reaction that we're going to sort of talk about here is zero order reactions. And in a zero order reaction, it is a little bit different in a sense, but here, do that here. Here we can get basically a zero order reaction by having one reactant that is to the zero order. And that basically means if we write the rate law will actually equal the rate constant. And that means that the units that we associate with the zero order reaction is actually the same ones that we see for rate, which is molarity over seconds. So if you see molarity over seconds for the rate constant, you know you are dealing with a zero order reaction. It has a rate law that's very similar to our first order, except no natural logging happening here. So basically the final concentration equals the initial concentration minus K, which is our rate constant, times T, which is our temperature. Once again, you could rearrange that equation like we did with the others, where A is equal to negative KT plus the initial concentration. And once again, that is going to give you your equation in the form of a straight line. y is equal to mx plus b. And that means on the y in this graph, we do take the concentration. On x, we do time. And again, the slope of this line is going to be a negative sloping line, which means the slope will actually equal negative of the rate constant. This again is going to give you kind of that negative equals a negative, which will turn your k into a positive. So again, positive value for k in this particular case. Now, when you look at that graph, you may say to yourself, I feel like I've seen that graph before. And you would be right. We saw a graph like that, or those two things graphed, when we looked at a first order reaction. But in a first order reaction, it did not give us a linear relationship. It gave us, right, that the concentration was decreasing with time. So it wasn't a linear relationship for first order. So if you see these two things graphed and it is not a linear relationship, but looks more like what I just drew there or what we saw earlier, it's probably the first order version of this graph. If you do this graph and you hit a linear line pretty much, it's going to be probably for zero order graph. I would say probably 9 times out of 10, if you see that graph, it's probably for zero order, to be honest with you. But again, if you see it's not really a linear relationship, but more that decreasing with time, then it may actually be the first order graph that you're looking at. But probably most of the time, you're going to probably see this graph here on the bottom and have that linear relationship. Just like for second order and first order, there is a specific half-life equation that goes with it. And that is the initial concentration divided by 2K. Once again, here, our zero order reaction is initial concentration does affect the half-life. In this case, right, since that's on top, I would imagine that if we have a larger concentration, we will end up with a longer half-life, right? Bigger number up on top. And vice versa, if we have a smaller number up on top, we'll end up with a smaller half-life in this sort of relationship. Now, when we look at this, again, the same things you should know are units associated with zero order, integrated rate law, half-life, and once again, our graph that goes with it. By the way, if for some reason you forget the half-life equation or something like that, but you're okay in math and you could do math pretty well, you can always, in each of these sort of equations for first order, second order, and zero order, you can just substitute into here basically the initial concentration divided by 2, and you can solve for t, and that will give you your half-life. So you could always, if you wanted to, I don't know why you would want to, but if you couldn't do it and you're in trouble, you could mathematically just solve for t in that equation at that point, and that would give you the half-life equation. So you could kind of do that as well. Any questions on that there? Let's give one a go here. Second order in Q. If we have an initial concentration of Q is 0.01 molar after 5 times 10 to the 2 seconds, and Q is 0.001 molar, what is the rate constant in this case? Otherwise, we would not know what it is. That will point us to our second order rate law here. And in this case, we do have the initial concentration given to us of 0.01 molar. We do have our time, not rate constant, but our time is 5 times 10 to the 2 seconds. We are looking for our rate constant here, and we have our final concentration of 0.00, too many zeros. Try again. All right, so 0.010 molar here. So we'll put in our numbers here, 1 over our final 0.001 molar equals 1 over 0.01 molar. And that's going to be plus our K, which is what we're looking for, and our time here, which is 5 times 10 to the 2 seconds in this case. I'm going to basically divide that on this side. Then I'm going to bring this over and subtract it. Now, so if you do that, Going to go 1 divided by 0.001, hit equals, minus, open a parentheses, maybe 1 divided by 0.01. That's going to get me a 900 over here. 1 over molar, basically, is our units, equals KR5 times 10 to the 2 seconds. At this point, we could then just divide that to the other side. So do a little division action, maybe. And that will get us a 1.8. The units here, 1 over molar seconds are, again, m to the -1, s to the -1, if you want to kind of go that way with it. Any questions on that calculation there? All right, let's try then one more here. How many minutes would it take A to go from 1.25 molar to 0.433 molar in this zero order reaction? The half-life of A is, I scribbled it out, but I guess I ended up with 22 hours. Let's try that. Popped up on this slide. Why not do it? Let's see. All right. See what you got to end up with here. Okay, so let's take a look, see how you're doing. So this one obviously is zero order, so we could just get our zero order sort of formulas out. And we also have our half-life there of our initial divided by 2K, I believe. And if we are looking for time in this case, right? How many minutes, basically? We'll take the concentration of A to go from, so that is our initial concentration, 1.25, to our final concentration, which is 0.433. And they do give us the half-life here is 22 hours they ended up with. So in this case, we are looking for this guy. We do have this one and this one. In this case, though, we are missing the rate constant. And that is where we will need to use our half-life equation here because we actually do have the half-life. So that will allow us to actually solve for the rate constant. So if you rearrange that half-life equation for K, this guy and this guy basically just switch places, basically, right? Multiply the K to the other side, divide the half-life to the other side. So this kind of switch places, and you end up with the initial concentration equals 2 times the half-life, right? So just basically swap places. Again, you're multiplying K to both sides and then dividing the half-life, basically, to both sides as well, man. So those cancel, those cancel. All right, so you do also have a choice at this point. I ultimately want my time to be in what units? Minutes. Right now, my time's in hours. So at some point, you have to do a conversion. So you could either convert it up front into the right unit so everything's good at the end, or you do have to remember to actually convert it at the end. I would probably recommend doing it up front because at the end, sometimes people are just happy to do the calculation, put a box on it, and you got the wrong answer, right? So I'm going to convert my hours here, obviously, into minutes. So at the end there, I know everything's good to go. I just need to box it. That's 60 minutes, I hope, still in an hour. So we'll go 22 times 60, not 61, 1,320 minutes. So I'm going to pop that in there. Now, obviously, if you kept it in hours, your numbers here will be a little bit different than mine. But at the end, it all should be the same, hopefully. So 1,320 minutes. So if I do all that there, we're going to get 1.25 divided by 2 equals, and divided by 1,320 and equals, going to get us 0.000473 units here. Obviously, going to be our molar our minutes in this case, not seconds, but molar minutes in this case. At this point, we now have everything we need to solve for what we're really looking for. So our final concentration, 0.433 molar. Our initial concentration there, 1.25 molar. our K value there, 0.000475 molar minutes, and our time. So again, I'm going to take this guy to the other side and subtract. Then I'm going to come back and divide that guy to the other side along with a negative. Yeah. So I'm going to go 0.433 subtract 1.25, hit equals, divided by our 0.000. Actually, I'll just use that number that's in my calculator there. I'll just use the whole number, which is right there, I think. And we'll divide that by 0.000474. And the negative as well is important. And if you do all that, your time will end up being about 1,726 minutes in this case, and maybe 3 sig figs everywhere-ish. So we'll go 1730. Could even probably go 2, but we won't go that far. Any questions on that calculation there? So again, very commonly, you sometimes will have to use that half-life equation. And again, in a lot of cases, this is what you probably use it for to get the K value. And then you have to use that integrated rate law to solve for whatever you're looking for, be it a concentration, a time, or whatever it may be. Any questions on any of those calculations there? So obviously, as I mentioned before, you do need to know those formulas. They will not be provided for you. So make sure that you know them for the first, second, and zero order ones. And obviously the graphs to go with it. This is a nice little table that does kind of summarize all those formulas together. And again, we have our integrated rate laws and our half-lives that go with it. As we talked about before, we also can determine the order through graphing, and that's also a very common procedure in kinetics experiments. Like I said, the second kinetics experiment, you'll do a bunch of that. That's basically how you'll determine in that experiment the orders of the reaction is actually you'll be doing these 3 different graphs. And once again, if you do graph that concentration versus time, and it does yield you a linear graph in the negative direction, that's going to be your first order. I'm sorry, not that's actually going to be your zero order. That's actually opposite here. That's to be zero order there. If you graph your natural log of A, again, versus time, and it also yields you a straight line, that will be your first order. And again, the slope in each of these cases is equal to negative K. So again, that negative is important so you don't get a negative value for K. And lastly here, that guy there, we have our 1 over A versus time. That's going to yield you a positively sloping line, and that would be the slope is equal to K, and that would be our second order in that case. So graphically, you could kind of determine if you have the right information. Also, obviously, mathematically determine it as well. Any question on those orders there? Okay. All right, so the next thing we're going to talk about is actual, go back maybe, there you go. Next thing we're going to talk about is the relationship between temperature and energy and the rate of a reaction. So as we talked about earlier, if you increase the temperature of a reaction, typically speaking, you will increase the rate of that reaction. Again, if you kind of double the or raise a lot of reactions by 10 degrees Celsius or so from where it started, it oftentimes will double the rate of the reaction and make it occur faster. What happens when you do that, obviously, when you increase the temperature, you're actually adding a lot more energy. That's going to give a lot more reactants a greater proportion of energy that will allow them to get to the other side, kind of the finish line, if you will, to get to the product side of the reaction. Opposite is true as well. Obviously, if you decrease the temperature, took all your test tubes and threw them on ice and cooled them down, you'd be like removing energy from the reaction, right? And what that's going to is probably a portion of molecules that have enough energy to get up and over basically to the. When we talk about energy, we talk about 2 types of processes. One's an exothermic reaction, one is an endothermic reaction. These are energy diagrams, and here we have our reactants going to our products in this case. And over here, we have our reactants going to our products on that one. And in this particular case, on the left-hand side, this is an exothermic reaction. So remember that in a chemical reaction, right, the only thing that happens is we break bonds, right? So that's all we do, basically break bonds, make bonds, rearrange everybody in terms of where they're attached to. So as this reaction progresses, what ends up happening is this reactants are starting to kind of break bonds and also make bonds. So they're breaking bonds and they're making bonds as they go up and over the hill here to get to the other side. This hill, by the way, from where the reactants start in energy to the top of the hill, that is what is known as the activation energy. And the activation energy is the minimum amount of energy that's required for a reaction to take place. There's really kind of two things that has to happen for products to be made. They actually has to hit each other, right? And they actually has to hit each other in the correct sort of location. And they need to hit each other with basically the right amount of energy. So not all collisions, just a simple act of two things banging into each other will not always lead to products being made. So they actually do need to hit each other, like I said, in that right location, like the active spot, if you will. And they naturally has to collide with the right amount of energy to get up and over that hill to the other side. That right amount of energy is the activation energy hill, basically that amount of energy basically to get to the other side. So when we get to the very top of this hill, right here at the very top of the hill, that is what is sometimes referred to as a transition state. And you can see this guy with this little kind of symbol on top of it. This is what is sometimes referred to as a transition state complex, or sometimes what is referred to as an activated complex. By the way, in this reaction, right about there where I'm drawing that big circle at the very top of the hill is the highest point in energy in this reaction, right? So in chemistry, do things like to be in high energy or low energy? Are things more stable and high or low energy? Low energy, right? Pretty much everything that happens in chemistry is all in the effect of in terms of energy to try to lower the overall energy of everything. Bonding, right? Making bonds, breaking bonds, how things come together is to kind of minimize the energy. So in this point, the transition state is really the highest point in energy you have along this process of this reaction. And that means that that transition state complex usually is something that has partially made bonds, actually broken bonds at that point, and it's very unstable. And usually what will happen is this guy will relatively quickly kind of drop to the other side. It's usually a lot of times very hard, for example, to isolate. If you want to isolate what's there at the transition state, it's very hard because it's really high in energy and not very stable. So it doesn't stay there very long. It kind of breaks apart because it's got these partially made bonds, partially broken bonds that goes to the other side. What we see is this is a exothermic reaction, right? Because our reactants are higher in energy, right, than our products in this case, right? And the only way for our reactants to get down to our products is overall energy needs to be released, right? And that is what an endothermic process means. Energy is overall released in a reaction. By the way, if I take the difference between the energy of my reactants and the energy there of my products, if I take the difference between those energies, that is equal to what? Delta H, yeah? That's the change in enthalpy of a reaction, right? You could calculate the change in enthalpy, as you may remember, hopefully. The change in enthalpy is calculated by taking the delta H of your products minus the delta H of your reactants, right? Add up all your products, minus them from all your reactants, right? It is because it's like a state function, right? The only thing that's important is where you started and where you ended, right? So in a chemical reaction, your final state is basically your products, right? And where you started is your reactants, right? So it's basically as products minus reactants, final minus initial in this case. And if you just think about it mathematically, right, in an exothermic reaction, my products are a smaller number in energy than my reactants. So if you take a small number minus a larger number, you end up with what type of number, positive or negative? You end up with a negative value, right? And that is why when we see a delta H value that is negative, it indicates that the reaction is exothermic. And that's usually how you will know if that reaction is endothermic or exothermic, is by the actual sign of the delta H of the reaction. If it is a negative value, then it is going to be exothermic. Any questions on that there? Now, if we look at the endothermic diagram, it's sort of the same situation happening. We have our reactant crawling up this hill, breaking bonds, making bonds, getting to our transition state up here. And in this case, this is going to be our activation energy, this big hill right here that they have to climb. And again, it will most likely come down that hill pretty quickly at that point to get to our products. This guy on the right is an endothermic diagram because our reactants are lower in energy, right, than our products. So in order for our reactants to get up there in terms of energy to our products, energy has to be put in, right? Our energy has to be absorbed. And that is pretty much your definition of endothermic, right? Energy is absorbed. You also could calculate the delta H by taking the energy of your reactants and your energy of your products, taking the difference. Delta H in this case will actually be a positive number because if we come down here to the bottom, in this case, our products are actually a larger number than our reactants in terms of energy. It's a smaller number. So when I take a larger number minus a smaller number, I end up with a positive value for our delta H. So again, that is basically how we know it is an endothermic reaction. The activation energy is the hill that you have to climb to get to the other side. It definitely has a big effect on the rate of the reaction, right? So if there is a large activation energy or hill that the reactants has to climb to the other side, that reaction is going to go fast or slow. Most likely is going to go relatively slow, right? There's going to be a smaller proportion of molecules that have enough energy to get over the big hill, right, to get to the other side. Rather than if you have a reaction where the activation energy is really small, there's probably going to be a greater number of people that could get up and over to the other side a lot easier. That's going to relate to a much faster rate. So I may have used this example before, but again, if you had to walk like a mountain up and down to the other side, that's going to take a lot longer and less people are going to want to do that, rather than if you just found like, a little hill that you had to climb over to the other side. More people are going to be able to kind of go over that like a speed bump versus like a big giant mountain or something that you're climbing. One of the ways that we can increase the rate of the reaction, by the way, we can see here just from these two diagrams, which one has the greater activation energy? The endothermic one does, right? Also makes sense since overall you need to put energy in to do that, right? That's going to kind of help people get up and over the hill versus an exothermic reaction where maybe we got some excess energy going to be. That also that we can speed up the rate of the reaction is we essentially can use a catalyst, right? And if we use a catalyst, again, it is not a reactant, as I might have said before. Again, it's not a product. And again, it does not get used up. In the reaction. It is there again just to simply facilitate that reaction happening in a more efficient. Again, that could be something as simple as we talked about, perhaps that it's just a piece of metal, right? And again, you got some gas molecules that may actually be attracted to that metal. That's just going to put everybody closer to one another and allow them to start reacting a lot easier. It could also be something like an acid used as a catalyst, where the pH environment allows things to come together a lot quicker and react a lot quicker. But ultimately, it finds a more efficient way of doing so. So to my mountain sort of example, instead of going up and over the mountain like the old cartoon, like the Roadrunner, right? Finds a trap door, just goes straight through the mountain to the other side, right? And it gets there obviously quicker. So ultimately, by finding this more sort of efficient way, what a catalyst is able to do when we look at these diagrams is it's actually able to lower the activation energy. So a catalyst can lower the activation energy. And thus, by doing so, that's going to create a situation where you're going to have a greater proportion of molecules now that could get up and over that smaller hill. And that's going to, in turn, allow your rate of your reaction probably to increase. And that's usually what we talk about when we talk about a catalyst, is the idea of increasing the rate of reaction. There are catalysts that are actually used to slow down reactions, and there's situations where maybe you wouldn't want the reaction to occur really quickly. But I would say in 99% of the time, if somebody's talking about a catalyst, probably they're talking about it in terms of increasing the rate of the reaction rather than necessarily slowing it down. A catalyst that increases the rate of reaction is sometimes referred to as a positive catalyst because it's increasing the rate. And a catalyst that can slow down a reaction, for example, is something that's referred to as a negative catalyst. So it kind of keeps it under control. You know, to an extent, if you think about nuclear chemistry, for example, in a fission reaction, neutrons basically feed a fission reaction. And you can use something like in a nuclear power plant, what are known as control rods. And what they essentially do is take out neutrons. And what that does is essentially will kind of slow down that reaction because they're removing the neutrons that are needed basically to keep that reaction going. So sometimes there are things that you could kind of put in there, like cadmium does that, for example, it will absorb all those things. Your catalyst is going to probably be thought of as speeding up a chemical reaction. Any questions on that there? All right, we'll let up there for today. If you didn't sign the